Hello friends, good morning, good afternoon and good evening. Welcome back to my channel. As I committed, let's start with the new learning. Today I'm gonna have a conversation with you on a new topic and the topic is CAN termination resistance. If you see my previous knowledge sharing session on the CAN fundamentals, I talked on the CAN termination, but today I'm gonna cover this topic more in detail. But to see why we need 120 ohm termination resistance in the CAN network, we need to go through the different topics. And this is my plan today. So we need to go through the CAN structure, and then we need to understand the basics of the transmission line, characteristics, impedance of the transmission line. Then we'll touch base to the CAN physical layer. Then we'll see what is the need of the CAN termination. Then I will talk on the termination methods and why this 120 ohm, what is where this magical figure is coming from. Why only 120? Why not 60? Why not 80? Or why not 200? That I will cover. And then we'll also talk on the debug methods. My focus for the debug method is only on the physical layer. I will not talk on the different errors in the CAN. I will just talk on the errors associated with the physical layer. So let's start with that. So initially, we'll talk on the CAN structure. So why I introduced the structure again here, the reason is before jumping to the CAN termination, we need to understand the structure as well. This is how the structure look like. Here is the node, another node, here is again another node, and it is connected with the help of the CAN bus to the network. So this is a CAN bus, and these are the CAN termination resistance on the both ends. Inside the node, there is a microcontroller, then the CAN controller, and the CAN transceiver. Here, your application code resides. Many of the microcontrollers have system-on-chip CAN controllers, and some have the standalone CAN controller on the PCB or the ECU. So this is how it looks. And this is like microcontroller, main microcontroller unit, CAN controller, and the transceiver are also inside this node. I'm referring node here as a ECU. And this communicate with this CAN bus. Uh, and these are the termination registers. So this is a CAN structure basically, as or sometimes you call as a CAN network, how the CAN communicate or the different ECUs communicate into the network. So let's talk on the transmission line. Basically, transmission line. Why we are talking the transmission line? When we talk about the termination resistance, it's all about the CAN bus, and CAN bus is basically is a transmission line. So we need to understand the fundamentals behind the transmission line. Suppose you want to transmit some signal, and that is a voltage source. Um, so this is a voltage signal you want to transmit with the help of this voltage source over some distance, and that signal needs to travel some distance, some XYZ meter or kilometer over your transmission line. So ideally, what we expect when we measure that signal at the other end of the transmission line, we always accept whatever the amplitude or the power ratings are associated here at the beginning of the transmission line in that signal, we expect same at the end of the transmission line. But if the transmission line is open at the other end, then ideally it does not happen. Over the time or over the distance as the signal travels, actually signal deteriorates or disturbs. So actually the amplitude falls down, signal becomes weaker. So this is the transmission line basically. Now, what is our expectation? Whatever the input voltage or the signal with the power, same we are expecting at the output, right? But as I explained, it ideally does not happen. When it works, when we have the proper termination at the other end. So there is a funda that term is called characteristic impedance. And this term is very important when we talk about the transmission line. And CAN is a transmission line basically. There are two wires that transmit the signal from one end to the other end. When I refer one end, that means the one ECU. So it takes some information, signals, messages from one ECU and transmit that information to other ECU. So it works as a transmission line. So as I explained earlier, if we don't have the termination, we cannot expect the input voltage or the whatever the signal with some amplitude or some electrical characteristics, we cannot expect the same at the output end. We need to have the termination to be done. And the termination is associated and related with this characteristics impedance. So this is my voltage source, right? And typically, uh, the circuit model describe the transmission line is a RCL model. So voltage source is connected to the transmission line. This voltage source is connected to the transmission line, and transmission line has a DC resistance, or I would say simply resistance, and also has some inductance. Now just imagine this transmission line has a two wires, right? So transmission line is made from the copper. This cable is made from the copper or some other material over some ground plane, and the two wire, this wire and this wire, form some capacitance as well. So here I'm also bringing the capacitance. So this RLC model basically defines the transmission line. So it consists of the resistance, and the resistance is measured uh, ohm per meter or inch or kilometer, whatever the unit or the signal which you want to transmit, the distance actually based on that the unit is. This is inductance, Henry per meter, and this is the capacitance, microfarad or nanofarad per meter. So here, when we send some input or the signal at one end, what we expect at the output? Output is basically the current is transmitted through the circuit and the characteristic impedance of this circuit. So here the characteristic impedance of RLC model, typical circuit model describe the transmission line is basically RLC model, and characteristic impedance of the transmission line is calculated from the equation square root of R square plus XL minus XC square. And this is a characteristic impedance of the transmission line. R is a resistance. This is a impedance, right? These both terms talk about the inductive impedance and the capacitive impedance. So this is how the characteristic impedance is calculated with the help of this equation from the transmission line. Now let's talk about the physical layer. What is the physical layer? So basically when I say physical layer, I generally refer the CAN network. This is one issue, this is another issue, and these are the other issues. Just imagine this ECU and this ECU. If the distance between the two ECUs are higher in the network, then the connection between the two ECUs are called a main backbone. So suppose this ECU and this ECU forms the longest distance in this network, then this and this is called a main backbone. That is very important to understand the definition of the main backbone. And the ECUs are taken out from the main backbone or connected to the main backbone is called stub length basically. So this is a stub length. So CAN bus is basically a twisted pair cable. CAN bus is a differential bus. Each differential pair of a wire is a transmission line. And we need a characteristic impedance of a CAN network basically. And I explained earlier how we calculate the characteristic impedance. So maximum CAN bus length limited by the baud rate. It is always depend on the baud rate. Baud rate, you are sending the messages into the network. Higher the baud rate, it reduces the total CAN bus length. And when I refer the CAN bus length, it is for the main backbone length. So the CAN bus length, basically, when we use the 1 Mbps of baud rate, it is a 40 meter. When we use 500 kbps baud rate, it is 100 meter. And if we use 250 kbps of baud rate, then we can have the 200 meter of the main backbone length. And for the 125 kbps, we can have the 500 meter of the baud rate. 500 meter of the main backbone length. So this is how the bus length is dependent on the baud rate which you are using in the network. So maximum stub length is 1 meter to 3 meter. Now why I'm referring this everything or I'm explaining here, because when we go for calculation of the characteristic impedance, all this length and everything matters. So let's see what is the termination need basically. Okay, so if the transmission line is open, then the signal reflects back basically. So when you send a simple signal across a wire, says a microcontroller output going from 0 volt to some 5 volt or 3.5 volt or 4 volt. Along a longer wire, the waveform will distort. The edge will become weaker, stuff like that. The result is more or less that you have to wait for the everything to stabilize before you reading the data information. So that is important as I explained. Signal get deteriorated, signal get weaker at the other end, because the end of the transmission line has to be terminated with the characteristic impedance of the transmission line itself. If the line is not terminated, when the signal travels to the other end, it bounces back or it reflects back and creates a standing wave. So this is very important. For this reason, we need a termination. So if the transmission line is open, the signal reflects back. And to avoid the loss of the signal, transmission line must be terminated with the characteristic impedance of the transmission line itself. So any termination that does not match the characteristic impedance is causing the reflection, and the worst case is a short circuit or the open circuit behavior of the transmission line, so which leads the malfunction of the entire network. So we need a characteristic impedance of a CAN network. So let's see what are these all points are leading towards the need of the termination. If we don't have the termination, if we have the transmission line open or our CAN communication or the CAN network is open, definitely there would be the effect of the signal reflections, and it will not have the proper communication. So let's see what are the different termination methods. So there are three methods basically. There are three methods to terminate the CAN bus, such as a standard termination, split termination, and bias termination. So bias termination basically derived from this split termination. So sometimes it is referred as a biased split termination. So standard termination method is the most common termination method, and which basically just places the 120 ohm termination resistance at each end of the CAN bus as shown here. You see here, we just have to place the 120 ohm termination resistance at the both end of the CAN network. Instead of saying the CAN network, I would refer uh, into the main backbone. So here we have to place the 120 and here the 120. So this is very simple network and it is very commonly used termination method. So now that's the standard termination method. As I mentioned, it is commonly used and mostly used. It's a simple network. But nowadays, the split termination method is gaining the popularity. It allows reducing the emission. And in the termination method, at the end of the CAN bus, usually we use 60 ohm of the termination region. We split that and we use also um, the capacitor in between. So, but to understand before jumping for the split termination, the bias split termination method is also similar to the split termination method, which except that the voltage divisor circuit and the capacitor are used either end of the CAN bus network. The standard termination consists of a single register termination between the CAN H and CAN L, which I just showed you earlier. And this technique entails placing the single register that matches the cable's differential mode characteristic impedance, which is actually the 120 ohm between the CAN H and CAN L. So if I, instead of jumping to the split termination, if I refer to this standard termination, we have to just remember that this 120 ohm are required to place at the both end of the network. So some applications that the space or the cost constraint do not have very stringent EMC requirements may go for the standard termination. Right? If you don't have any stringent requirement on the electromagnetic interference or EMC requirements, then definitely we can go for the standard termination. Now let's say the split termination. Let's talk about the split termination. So a split termination basically consists of two identical registers, that is a 60 ohm registers and the one capacitor. The typical value for the capacitor is approximately 4.7 nanofarad. And this combination, if we look at the figure, these 120 is splitted into two resistors on the both end, and it is splitted with this capacitor, right? And grounded here. So this R and C forms the low pass filter. High frequency signals are shunted to a ground without affecting the voltage relationships. The last thing that you need to consider when selecting your termination register is how to size them. Depending on the fault that can occur in the system, the registers needs to be rated to handle possible fault currents. The usual worst case fault would be to have a supply wire shorted to CAN, where the CAN would cause a large current when driving a dominant signal. For 12 volt supply and 120 ohm impedance, the register could have such a much as 200 to handle around approximately 100 milliampere of the current throughout it. It is therefore important to use the register with a power rating high enough to handle the possible bus fault conditions. So what will happen if we use the 12 volt of supply and considering this 120 ohm impedance, maximum possibility to have 100 milliampere current flowing through the network. So power rating of this resistance are important, not only the ohm ratings. We need to take care of the power rating as well. The split termination technique shown here uses the two registers that are equal to one half of the cable's characteristic impedance. And as I said, it's a 120, so it's exactly half of the 120, that is typically 60 ohm each, with the capacitor placed between the common mode point and the ground. Here is the common mode point, and here is the ground. So capacitor is placed between the common mode point and the ground on the both side. This is a typical value, but based on the requirement on the cutoff frequency, that is FC is 1 by 2 phi RC. Actually, that is the formula for the cutoff frequency. It's fundamentals of the transmission line when we talk about the cutoff frequency. So there, based on that, we can choose if there is a need of some specific frequency, you can opt for, but R is constant. You can vary the C value. And this value typically varies from 1 nanofarad to 100 nanofarad, but it is in the nanofarad. Okay. Although the split termination technique uses more component, it offers the added benefit when we compare to the standard um, termination. In standard termination, we are just using 120 here and 120 here, right? But here we are adding some components. So cost gets added here in the split termination. But what are the advantages? It offers the different advantage of creating the low pass filter for common mode noise on the network, and thus can add in improving electromagnetic emissions. The resistor and capacitor create an RC low pass filter. One thing to keep in mind with the split termination is that it is important to use well-matched registers. Any variation in the resistance will convert the common mode noise present on the network into the differential noise, thus compromising the receiver's noise immunity. So just matching with the resistance value will not work. You need to match their other ratings as well, like the power rating. That is important. If there is a small variation, definitely there would be noise immunity at the receiver end. There, there should be the noise immunity compromise at the receiver end, right? So this is all about the split termination. So let's talk on the third method, that is a biased split termination. So biased split termination method is similar to the split termination method, except that the voltage divider circuit and a capacitor are used at the either end of the CAN bus that's shown here in the diagram. Okay. So additionally, circuits are added here. It is pulled to the voltage source, and this R1 and R2 are splitted here. This is how it is taken from the split termination method, but these two registers added, and already the capacitor was taken from the previous method, that the split termination. Biased split termination is usually done in the context of improving EMC performance. If you want the better EMC performance, then we need to go for the biased split termination, or we can call it as a biased termination. The 60 ohm termination register cannot be changed, but the R1 and R2 in the biased split termination could be sufficiently large. So we need to take these values in the kilo ohms or higher than that. We cannot take like in the ohm values. This makes sense since with just an additional these two components, the termination network becomes an effective filter for high frequency common mode noise without degradation to the differential mode signaling. That's the benefit of the bias split termination compared to the split as well as compared to the standard termination method. So I have summarized everything. So let's um, talk on the summary on the termination methods. Three termination methods: standard termination method, split termination method, and biased split termination method. In standard termination method, we just used 120 ohm at the both end. In split termination, we use we use 260 60 ohm termination resistance, and on the uh, uh, top of that we add the capacitance, and the approximate value for the capacitor is around 4.7 nanofarad, and it depends based on the need of the filtering effect into the network. You need to vary that value of the capacitance. And in bias split termination resistance, um, this method is similar to the split termination, except the voltage divider circuit is added there along with the capacitor used in the either end of the CAN bus. So that is all about the summary. So let's talk about the major points in the summary to the termination methods. So standard termination method is the most commonly used termination method. What are the reasons? The reasons are it is a simple, low cost, and very less complex method. So split termination method allows reducing the emission and unwanted high frequency noise filtered from the CAN bus line. That is the benefit of the split termination. The bias split termination uses the voltage divider and the capacitor to increase the electromagnetic compatibility performance. That is the benefit of the bias split termination compared to the split and the standard. In the bias split termination, depending on the fault that can occur in the system, a resistor needs to be rated to handle possible fault currents. We need to take care of uh, the, the ratings of the registers also. In biased split termination with the additional components, termination networks becomes an effective filter for higher frequency common mode noise without degradation to the differential mode signaling. That is very important. These are the beauty of this bias split termination. But if you see the cost is associated with this high as well as the complexity is high. Now, till now we have covered the standard termination, split termination, and bias split termination. So let's talk on why we need 120 of the termination resistance. So termination resistance should match with the characteristics impedance of the bus line used for the communication itself. That is important. Otherwise, we will have the signal reflections and the signal bounce back. That would happen. Now, important part is that when we go for deriving this value or calculating this value, the geometry involved and the material, sometimes the copper is frequently used material is copper. So geometry and the material used for the transmission line determines the exact value of the characteristics impedance. Both are important. Now, if we take few example for other bus communications or other cables like coaxial cable, the termination resistance value falls between the 50 ohm to the 75 ohm. It never crosses beyond that. For the Cat5 cable, it is officially announced that is the 100 ohm. So, so for CAN, considering the maximum baud rate with a possible CAN bus length of 40 meter, these are the important point which leading towards why we derive this 120, how this magical figure come from the 120. So in the CAN, we know that uh, the main backbone length or the CAN bus length is limited by the baud rate. Higher the baud rate, lesser the length. Lesser the baud rate, higher the length. But we are considering the maximum baud rate here. That is the worst case scenario. And so we can have the maximum bus length of 40 meter, right? So for CAN, considering the maximum baud rate, or let's say we have considered the maximum baud rate. Now talk about the minimum baud rate. If we consider the minimum baud rate, that's 125 kbps, then we will have the 500 meter of the bus length. Now consider the worst case scenario, the maximum stub length that is varying from 1 meter to 3 meter if we consider 3 meter, and the maximum backbone length up to the 40 meter with the baud rate of 1 Mbps. So all these points which are important, like material use, the geometry use, the baud rates and the bus length, everything leads towards a derivation of the characteristic impedance. So considering the worst case bandwidth, worst length of the CAN bus, and the material used for the cable, maximum twist allowed per meter into the stub length as well as into the main backbone, and the maximum possible operating voltage used, and the maximum high frequency signals are introduced into the CAN network. If we consider everything, then if we assume if we assume there is a capacitive reactance present into the network as well as the inductive reactance present into the network. If you remember, I just covered a few minutes back um, the RLC circuit, which is a basically um, uh, it's talk about the transmission line. Basically, is a reflection of the transmission line, right? So in the RLC circuit, if we consider the resistance as well as the impedances, both impedances, we are assuming in our CAN bus we have a capacitive reactance as well as inductive reactance present into the network. And considering all this point, the characteristic impedance or the effective, sometimes it is called as the effective resistance of all that network or the bus components in the CAN bus line never cross the magical figure of 120 ohm. So total characteristic impedance calculated from the equation Z is equal to square root of R square plus XL minus X6 square, whatever the value we will get will is not more than the 120 ohm. It's a worst case value. Considering all the worst case scenarios, what is the worst case scenarios? The length of the CAN bus, um, the reactances are present into the network, as well as the highest baud rate, high frequency signals are into the network. Everything considered the worst, and if we calculate the characteristic impedance of the CAN bus, the value never crosses this 120 ohm. That is the best calculations in during or considering the worst case scenario. And that is why, so in the CAN network, the termination resistance is 120 ohm. I hope now it is super clear for you why we use the 120 ohm, why not the other value? That is the reason. In the transmission line, we need to understand the behavior, the length, the signals operating voltage, what are the impedances involved into that. So considering the CAN application, it is not designed for the use of kilometers or more than that distance. It is designed to handle the 1 Mbps of baud rate, and some meters of the distance like 40, 50, or 100 meters of distance. So with that, if we calculate the character's impedance, the magical figure is a 120 ohm. And that is the reason the termination resistance in the CAN network is a 120 ohm. Now, let's talk about the debug methods. And when I refer to the debug method, I'm just talking about the physical layer. Because in a CAN, there are different errors: active error, passive error, warning states, as well as bit stuffing error, acknowledgement error. So many errors are there. But here, as today's topic is all about the termination resistances, it is restricted, or it is protected, or it is concerning more about the physical layer. So that's what the debug methods. I'm talking here all about the physical layer only. So both termination resistance are in parallel into the CAN bus network. So at the both end, it's 120 ohm. So what is the effective resistance present into the network is 60 ohm. If we use the multimeter and just tap one probe on the CAN H and one probe on the CAN L wire into the CAN bus network, then you can find the effective resistance is 60 ohm. But there is a method actually. You cannot directly go and just tap that CAN H and CAN L. So for that, you need to turn up the power supply. If you are on the test rig or on the bench, HIL bench, you need to turn up the power supply. And if you are in the vehicle, you need to turn up the vehicle ignition or the supply, battery supply, LV battery supply. That's 12 volt or the 24 volt based on your application. You need to turn up that supply. You need to turn up the vehicle ignition, and then with the help of multimeter, just check. Um, Initially, first step is to check the continuity. CAN H and CAN L should have the continuity. It should not be open. Check the continuity in the CAN H itself. Like pick up the one end of the CAN H and pick up the other end of the CAN H. Also do for the CAN L and check the continuity between CAN H and CAN L also. There should be the continuity. That should not be the open. That's the second checkpoint. The first you have to turn off. This is the checkpoint. Then what you have to do, you need to check the resistance present into the network, and that value should be in between 57 ohm to 63 ohm. Now, why this value? The reason is I explained here. Both ends are terminated with 120 ohm resistance. So effective resistance in the network is a 60 ohm. If we solve the two parallel resistance equation, that R1, R2, that means R1 into R2 divided by R1 plus R2, that means the effective resistance value will come 60 ohm. But practically what happens when you works on the vehicle, because of the diameter or the material used in the CAN bus or length of the CAN bus, the value varies. Many times you can find that value around 58 point something, or sometimes you can find the value of 62 point something or 59. You never find the exact value of 60 ohm, right? So if the value is between 57 ohm to 63 ohm, that means your termination is properly done. If you are getting the value around 40 ohm, that means some additional 120 ohm is into the network. Then you need to understand, you need to look for your CAN network, and then accordingly you need to check where the additional 120 ohms getting introduced into the network. So this is the checkpoint actually. So for if you are finding the value around 38 to 40, 43 or in that range, that means around the 40 ohm. Definitely, it is sure that additional 120 is introduced into the CAN network and your ECU will not work. So you need to make sure that value into the CAN H and CAN L is in between the 57 ohm and between the 57 to 63 ohm. So after power, now what we have to do, this is before power off, then you just have to turn on the power, provide the supply to your HIL or the ECUs which are connected to the network, make the power on, and now you have to use the oscilloscope and now to measure the voltages on the CAN H and CAN L wire. Measure the voltage between the CAN L and ground with respect to ground, and that voltage should be in between between the 2.5 to the 2 volt. That value should be approximately in this range. Again, measure the voltage on the can edge and the ground, and that value should be 2.5 to 3. This is the approximate value, so it should not fall out of the range. This and when the bus is dominant, there are two states: dominant state and the recessive state. Dominant state means logically 0, we call it, and recessive state means logical 1. So when it is in the dominant state, the differential voltage, the voltage between the can H and can L, should be greater than the 1.2 volt. It should not be lesser than the 1.2 volt, or even not equal to the 1.2 volt. This is what you have to debug if your network is not working. If you're doubting on the physical layer, you need to do with the help of oscilloscope, with the help of multimeter. And when your bus is recessive, the differential voltage should be in the range of 120. I mean, it should be greater than the 120 millivolt and lesser than or equal to the 12 millivolt. This is how in the recessive state, your differential voltage between can H and can L should be. And this is what I was referring the voltage level. This is a differential voltage I'm referring. So when this is a dominant state, so in the dominant, this is a can H and this is a can L. When the bus is a dominant state, the differential voltage must be greater than 1.2 volt. DC volt I'm referring here. This is a voltage and is the time I'm talking. And this is the signal getting transferred into the CAN bus. We have just punctured the CAN H and CAN L and used the oscilloscope probes and measuring that differential voltage. When the bus is recessive, if you see um, the color, this red is for the CAN H, green is for CAN L. And if we measure the differential voltage, that value is very less. That is, in terms of millivolt, it should be in the range of 120 millivolt to 12 millivolt. These are the common debugging methods used for the physical layer. If you find the voltage level are perfect and the resistance is around 60 ohm, it's in between 57 to 63, that is okay. That means your network is okay. And if still there is some communication error, then you need to check the baud rate. So that's a different, like you need to check for the errors. What are the errors present with the help of the different tools like Canalizer or Vehicle Spy? You need to look for that. So that's a different um, topic. But when it comes to physical layer debugging, mostly we check the voltage as well as the resistance. So that's all, I guess, for today I have to present. And I hope you like this session. And as I earlier mentioned that I always want to know what is valuable for you inside this session. And if you like my video, like my knowledge sharing sessions, please like, share, and subscribe to my channel. Thank you.